At the UW, I study fisheries management. Well, actually, I focus on mathematical modeling of fisheries to inform policy decisions. But as a graduate student, I get really specialized training in how to do a very specific type of research. The Engage program gave me another type of training that graduate students rarely get. I learned how to talk about my science in a way that is engaging, enlightening, and informative. You can learn more about our innovative program at engage-science.com. I get to have this opportunity because of the special collaboration between Town Hall and the UW's Engage program. Together, they host a series called UW Science Now. That's part of the Seattle Science Lecture Series. Sponsors include Microsoft and KPLU. I would also like to mention that the best way to keep up with Town Hall's events is to become a member. Membership offers down-front seating, discounts on book and ticket purchases, and a mailed copy of Town Hall's monthly calendar. And it provides the support essential to bringing you more than 400 annual events at affordable ticket prices. Tonight's speakers program will run about 25 minutes, including 5 minutes of questions after the talk. We ask that you come to the mics at the edge of the stage so that we can pick you up for the recording that we're making. Before I introduce our guest tonight, I'd like to mention some other events from the science series. First, please join us after Chris's talk for Chris Baldwin, who will discuss how you can find work that you're meant for tonight at 7:30 p.m. following this hour. Also, the next two talks in the UW Science Now series will be right here this Friday, May 20th at 6 o'clock. And I will be talking about caring by the numbers with Dr. Heather Fowler, also talking about backyard poultry. And now to our main speaker. Why do things melt? More importantly, does everything melt? Surprisingly, the answer is not necessarily. The explanation is not intuitive, but it represents one of the frontiers of modern physics. Chris Baldwin from the UW Department of Physics and a PhD student will describe the concepts behind this idea of un-meltable materials. What happens, what does not happen, and why it upends a lot of what we take for granted in physics. Please give a warm welcome to Chris Baldwin.
Yeah, well, thank you for the introduction. Feel free to move towards the center. It's an excessive space, and it's hard to compete with Beyonce. So, yeah, well, on that note, so I'm Chris, and like John said, I'm a PhD student at the University of Washington, and the specific area of physics that I work in is about how to describe big and complicated systems, the ones that are made of many pieces all moving simultaneously. Everything we see around us falls into this category because we know that matter is made up of lots and lots of atoms, all pushing and pulling on each other all the time. And one of the rules of thumb we have about big and complicated systems like this is that order naturally tends to become disorder. So my first goal for this talk is just to convey exactly what that means and how common a thing it is to experience. Now my second goal, on the other hand, is to describe an idea that challenges this, an idea that some materials might never become more disordered. And that's not because we would have to work to keep them ordered, mind you. It's because they, by their very nature, would just be incapable of falling apart. And we'll see that that's a very strange idea. So I want to begin with some more familiar experiences. And so what's familiar to us is things falling apart. You know, everything has this tendency to become messier, to become more disordered over time. You know, we've all experienced this, like our homes, right? Mine included, are good examples of this. And I'm talking specifically about what happens when we let nature take its course and don't try to intervene. You know, I can and do wash and vacuum regularly, and right afterwards everything is nice and clean. But from then on, dust and dirt start accumulating, and pretty soon I have to clean all over again. So having a clean apartment, unfortunately, is not the natural state, and we have to work hard to combat that. And so once you know to think about it this way, you start to see similar situations everywhere. Like our headphones, right? You know, you certainly aren't trying to tangle them up when you put them in your pocket. You put them in your pocket neatly enough, but they get jostled around throughout the day, and then when you take them out, they're in this mess. So Yeah, the reason is basically that there's lots of ways to tangle up chords if you aren't thinking about it. But you really have to make very deliberate and intentional movements to untangle chords. So when your headphones are just sitting in your pocket throughout the day, they're much more likely to get tangled up than untangled. And now a more physicsy example, which you may not be used to thinking about this way, is ice melting. So now this example is going to play a leading role for the rest of this talk. It'll be a sort of template on which I illustrate a lot of these ideas that I'm talking about. So I want to dig into it more deeply. I want to explain what exactly is going on when an ice cube melts and why this is an example of order becoming disorder. So here we have my best rendition of a glass of water without any ice cubes or other complications yet. To us, this looks like a continuous fluid, but the water, as is everything, is actually made up of atoms. Technically with water, the atoms are stuck together into molecules, but for this whole talk, that distinction between atoms and molecules won't actually matter. And I honestly will commit a small sin and use the words interchangeably. What does matter is that the atoms are constantly in motion. They're constantly pushing and pulling on each other. On an atomic level, water looks like this. So the takeaway here is that the atom's motion is very chaotic. They aren't synchronized at all, right? Each is trying to do its own thing while being shoved around by the others. So now let's put in an ice cube and ask what it looks like on an atomic level when this cube melts. Well, so initially, the atoms of the cube, shown in red, are very well ordered, right? They all hold each other in place. But as the mobile molecules of the liquid collide with the cube, they knock pieces off. And this keeps happening until by now there's pretty much no cube left, right? Now there's just water. So what's happened here is that the initial order of having these atoms in a well-arranged cube, it got kicked apart by the motion of the molecules around it. And so because of that motion, it got converted into disorder. So we have a word for this final state, the one of most disorder. We call it equilibrium. So the water after the ice cube has melted is in equilibrium. As stuff piles up in your room is reaching equilibrium in a way. And similarly with your headphones. Now we also call the process of becoming more disordered equilibration. So that actual process of the ice cube melting, that's an example of equilibration. And so now this idea of order becoming disorder that we encapsulate through the word equilibrium, it really is a fundamental part of physics. At the risk of being poetic, it's one of the pillars holding up this whole construction of science. And what I mean by that is that we're always taking it for granted that any system we want to study, it's either in equilibrium or equilibrating. But keep in mind that our confidence here is only based on what we happen to observe around us. There's no fundamental law of physics that guarantees that systems equilibrate. And so that brings us to the second part of this talk, which is how guaranteed is equilibrium? In the language of ice cubes, is it possible that there could be some artificial ice cube that would be incapable of melting? Well, what people are just starting to realize over the last 10 years is that it is in fact possible. So in a sense, this pillar of physics has some cracks in it. I want to emphasize just how strange an idea this is, because let's imagine that you take your favorite ice cube and you put it out in the sun, and then you wait, and the hours pass. But the ice cube never melts. It lives to fight another day, right? That's the sort of strangeness that I'm talking about here. These really are things that we don't experience in our day-to-day lives. And now to be sure, ice, like actual ice, certainly does melt. I'd feel bad if you went home and threw out your freezers. Please don't. The question is whether there exists, whether there even can exist some material that would be incapable of melting. And that's what I'm saying is in fact possible. So actual ice certainly does melt, there's no doubt about that. But the proverbial ice cube need not always. But really, we're used to everything melting. Even solid iron melts if you heat it up to over 2,700 degrees. So how could it be that something would just be incapable of melting, no matter how hot you make it? Well, the answer is very counterintuitive and, frankly, bizarre. And so to understand it, we have to take a break for a bit and talk about light, specifically how it moves. And so I admit this seems like a complete non sequitur, and for a few slides it will be. But with research like this, the most direct route is never the most natural one. And so we have to sort of weave around and take detours and make connections that way. I promise we'll get back to the original never melting ice cubes soon, but for now, we're going to think about light for a bit. So I took this picture on the way to SeaTac one morning, and you can see the trees outside the light rail. So mostly what you see is the reflection from inside, right? And if you look close, you can even see a reflection within the reflection. So the point here is that some light reflects off the surface of the glass window. And when not a lot of light is coming in from outside, you see that reflection really well. And this is even though light passes through glass just fine. Glass is transparent, right? We can see through windows. So schematically what's going on is this, that light comes out of some light source, and most of it passes through the window just fine into the outdoors. But a bit of it scatters off the window here and back inside. And our eyes pick that up, and that's what we see as the reflection. But I want to emphasize here that light passes through glass perfectly well. It's having that interface there, that boundary between one material and another, the air and the glass in this case, that causes some light to reflect backwards. If I were to take a very thick chunk of glass, much thicker than a window pane, light still only bounces off the very beginning and the very end, where the boundaries are. A good analogy is that the glass is like a different type of terrain for the light to move in. It's like running on grass instead of concrete. There's nothing that physically gets in your way, you just move somewhat differently. And maybe the first few steps are kind of uneven as you're making that transition, but once you get into it, then you're moving very naturally, right? And the same thing's going on here with light moving through glass. But now I want to imagine something. What if instead of taking a thick chunk of glass, we were to make a thick chunk by stitching together thinner chunks, each of which is slightly different, like here? Well, now there's many more boundaries between different types of terrain, right? And so if we send light through, well, some of it still gets lost at each interface. And in the end, a lot less makes it through to the other side. This is even though there's no more glass than there was before, right? What there's more of is interfaces. And so the lesson here is really about homogeneity, which basically means how uniform the material is constructed. So light passes just fine through homogeneous materials, those that are uniform throughout. But light has a lot of trouble getting through inhomogeneous materials, ones where the constituents are all slightly different in some way. So that's the lesson there. But what does it have to do with atoms and ice cubes? Well, and this is where it starts to defy our common experiences. But this circle here is my rendition of an atom. And one of the most important discoveries of the last 125 years, in all of science really, is that single atoms behave like light in a lot of ways, a lot of strange ways, including that they have some chance of reflecting off of the interfaces. You may have heard of the term wave-particle duality. If you haven't, no worries, because really this is what it's referring to, that there are a lot of similarities between how things like atoms and things like light move. And so to represent that similarity, my atoms are now going to have these light squiggles in them. But the more you think about this wave-particle duality, the more you realize that it's a very counterintuitive concept, because the world around us certainly does not behave this way. Imagine that you were to go out running, and most of the time you go from concrete to grass and back just fine, right? But then every now and then you just bounce backwards. And there wouldn't be anything in your way. It's like you would just hit this invisible wall just for trying to get off the street, right? You would be very unsettled if that happened, and understandably. Luckily it doesn't happen to people. We would have heard about it if it did, right? And the way to reconcile this with what I've just told you is that the light-like behavior, which does include bouncing off of what seems like nothing, that's incomprehensibly unlikely for any but the smallest of particles. So we're talking single atoms and small molecules. So an atom, moving in the atomic equivalent of varying types of terrain, does have a chance of bouncing back. And the chance is high enough that scientists even observe this in laboratories. So it's a strange idea, for sure. And really the best thing that I can tell you is that we see things like this happening with light. And it is a well-documented fact that single atoms happen to do the same thing. But now as for what terrain for an atom would actually look like, it's more subtle than just the type of surface that it moves on. You know, one of the most common ways that scientists have for creating terrain for an atom is through lasers. So if you played with a laser pointer, this laser pointer, you might be familiar with this speckle pattern. You know, basically when focused laser light, like what comes out of a laser pointer, reflects off of some rough enough surface, it does so in this very chaotic way. You get this chaotic reflected pattern. And so an atom that's moving through this speckled laser beam, it feels all this roughness. And so to the atom, it is like moving through inhomogeneous terrain. And the nice thing is that, you know, scientists are able to tune how speckly their laser beams are. And so because of that, they're able to tune how homogeneous or inhomogeneous the medium for the atom is. And so with this, if we go back to this animation of the stitched up composite glass, and how we think about a beam of atoms trying to transmit through a speckled laser beam, well, the same sort of thing happens. That some atoms bounce back at each interface, and very few make it through to the other side. And you know, because this is the most counterintuitive part, it bears repeating, and I will repeat it, you know, throughout the rest of this talk, that this isn't just a matter of the atoms not having enough energy to get through the beam. You know, it's not that they aren't forceful enough. These atoms are perfectly capable of getting through the beam. It's just up to chance whether they do or not, and it's because of this bizarre wave-particle duality that atoms experience. You know, so the issue here is not energy. And that's really the key to all of this. Now we get to start to come full circle and actually talk about those cubes. Because what if, instead of thinking about atoms transmitting through a medium, we think about atoms immersed on all sides in it, and ask how the chaotic sort of motion, like what we saw in that glass of water, how that changes. You know, in that simulation from earlier, there was no background. There was just water molecules interacting with each other. But we can imagine, and scientists do this in laboratories, recreating that same setup within one of these laser beams. And so what changes? Well, in a homogeneous background, so a laser beam that is not speckly at all, well, the atoms move just fine. Right? Just like light and glass, they're able to move perfectly well once they're in the medium. If the background's inhomogeneous, so somewhat speckly, well, now every now and then, atoms bounce off some of the interfaces, right? And now the key step here is, you know, what if the background were so inhomogeneous that it changed over lengths comparable to the size of the atoms themselves? So in that speckle pattern from a few slides before, what if each speckle was as small as a single atom? Well, in that case, it turns out that there's so much scattering that the atoms can't move at all. Basically, any direction they try to move in, there's immediately all these interfaces that chip away at them, with the result that they just can't go anywhere. And again, this has nothing to do with the atom's energy. You know, it doesn't matter how forceful they are, because this speckled laser beam, or whatever it is that the scientists are using to create this inhomogeneous background, it's not acting as a barrier to the particles. It's not something for them to get over. All it's doing is setting up this varying terrain that then exploits the atom's wave-particle duality. And so now it's a very short step to get to cubes, because let's just say that within our speckled laser beam, we put some of our atoms in a cube. Well, the atom still can't move, right? So that cube never disintegrates. You know, and the key, again, is because this effect has nothing to do with energy. It doesn't matter how much you heat up the cube. You know, when you heat something up, what you're doing is giving the particles inside more and more energy. But what we're finding in the present day is that there are these sorts of caveats to the standard physics, where having more energy does not necessarily mean that you can move any better. You know, and there are other things going on, basically, this wave-particle duality that can have very serious consequences, like in this case. You know, it doesn't matter how much you heat up these atoms, because they just can't do anything with the energy you give them. They're just incapable of moving. And so because of that, this cube is incapable of melting. And really, that's the idea behind these never-melting materials. And I admit that this specific setup I've described is very contrived. It's hard for me to see this turning into an everyday commercial application. but I want to emphasize the implications behind this idea. A lot of the things that we take as facts of life, like that heat flows from hot to cold, and that's how things melt, these are really statements about equilibrium, that systems equilibrate. And we've always just assumed that equilibrium's unavoidable, that that's where things end up and we just have to plan for it. Well, we're finding out only now that nature is a lot more complex than that. That even something seemingly mundane, like heat flowing, can actually be very bizarre and in potentially very controllable ways. So the big goal here, the long-term picture, is to find this sort of never-melting material behavior, not within a laser beam that scientists have set up, but within certain exotic materials. Because then once we have that, we can start creating things that until recently we wouldn't have even thought were possible. So on that note, thank you for listening, and I'll take any questions. Yeah, go for it.
In the original diagram showing the atoms crossing multiple boundaries,
Yeah.
they showed it crossing, say, 3 or 4 boundaries, and some atoms made it through the boundaries.
Right.
And you, I assume, arbitrarily said, well, after 3, none will make it past the last one. Okay. So there's some number that they can't go past.
Right.
And that last diagram, you showed little boxes.
Yes.
I'll say it's 2-dimensional, so there's, 6
Yeah.
surfaces or boundaries. Just like you showed them passing through, some molecules passing through the first couple boundaries, wouldn't a molecule inside one of those boxes eventually cross over and go to the next box? And so that, in fact, they could eventually kind of move around, and I assume since they're vibrating so fast, they would eventually move around and quote melt.
Well, yeah, that's a good question. Really, that's the question to all of this. Yeah, so, in order to study these sorts of things, that's basically what you have to account for. That's what you have to calculate is, what's the chance of an atom making it through 5 of these boxes, and how does that compare to the number of atoms you have, and you have to see what thing wins out in the end. And when you're talking about these boxes that are as small as the atoms themselves, this light-like behavior really starts to complicate things, and so you have to put it all together all at once. And what you find at the end is that there is some small region around which the atom can vibrate around, but you find that it's stuck in that region basically as you imagine a bigger and bigger system. So ultimately we would like to make some unmeltable material that we can actually see, that's macroscopic, right? And for a material that big, you find that this chance of things escaping becomes so small that it's pretty much negligible. Sort of a competition, right? And this is what wins out in the end. Yeah.
Great. So
Thanks.
I was just wondering, so the boxes in your example,
The boxes.
they're essentially like atoms as well, right? Like everything's made, all matter is made of atoms. So all of the theoretical boxes in some material that would be un-meltable would also be atoms as well, right? So how could you make an atom that's smaller than an atom, if that makes sense at all? How would that interface ever be smaller than an atom?
Yeah, no, that's good. Yeah, I was so this sort of effect shows up even when your boxes are as big as the atoms. It's really possible these days to make materials that are so sort of mangled up that each atom forming the material is very different from its neighbors, It sort of defies what we think of solids as being, as having this nice, simple structure that holds them in place. But you can make these sorts of dirty solids, or disordered solids they're called, that really have no structure like this, and yet still are like structurally sound. And in those sorts of things, then this picture of having a background that changes, at each atomic length, that becomes more accurate. Yeah, so it's a good question, though.
I'm looking for the fact that you specifically matter how you're judging,
Yeah.
which suggests that it would be terrific to start with that and charge it. I don't know what it is, but charge it. But I'm not
Uh-huh.
what other practical applications there's.
Yeah, right. So I know the thing that people are investigating right now, one of the things is for using this to store information, basically. Very similar to storing power. Basically modern computing, you hear that like the chips are getting smaller and smaller, and it's getting to the point where this wave-particle duality that I was talking about can become important. And people are trying to actually use that to their advantage to compute by taking advantage of this wave-like behavior. The caveat there is that these systems are very sensitive to noise. It's very easy to knock them out of place just by being in contact with some environment. And so this sort of behavior is a very ideal way to prevent that, to be able to preserve the information because there's no way for it to move anywhere else and get out of sync, basically. It's still a long ways away, the actual developing these sorts of systems. But those sorts of ideas in general are what people are interested in, being able to preserve the structures that they set up, even on an atomic scale. Yeah.
Does the model have to be thought of any differently if it's an atom trapped in a box versus like a molecule trapped in a box with the chemical bonds between molecules versus like independent atoms?
No, I don't think so. Yeah, as far as I know, people haven't investigated those sorts of questions yet, but I don't think there's any theoretical limitation to that. Well, thank you for listening.